Hello, Algebra 1 students, and welcome back to Topic 10, non-factorable quadratics, right? The point of this unit is to look at quadratics, ax squared plus bx plus c, that we can't use the box on. So today is a nice extension of lesson 10.1. Definitely make sure you've watched that one. And what we're going to do is try and get a visual of what's happening when we completed the square last class. In fact, we didn't even talk about why it's called completing the square, so we're going to get a more concrete understanding of what's happening behind the scenes and get a different way to complete the square than what we learned last class. And to do that, we're going to start with our algebra tiles. So you should have a set of algebra tiles nearby. If you don't, you can always draw them. We're not going to use them too much today, but again, the visual I find really helps me and my students. You should have 6 of those x squared tiles. Hopefully you have 10 of those x's and 25 of your 1's. If you don't, let your teacher know, and we can get going in just a sec. I'm going to do them electronically again, just on one of my web pages, and you'll see what I'm doing, and you can follow along in just a bit. So, what is our end goal for completing the square to solve standard form quadratics? Well, we want a nice handy-dandy formula that will complete the square perfectly for us every time. Math really should be about understanding why something works, not just memorizing a formula. So, why do formulas exist? Well, oftentimes problems get tedious. You're doing the same type of problem over and over again. You might have some difficult or gross numbers. And so that formula should help take the edge off of anything and make it go faster, right? It's an efficient way to do something. So what we're going to do is try to gain an understanding of the patterns that emerge when you complete the square. We're also going to understand what it means to complete the square. And then by looking at those patterns, we're going to generalize a process and come up with a formula that allows us to complete the square quickly and efficiently. So let's begin. Using our algebra tiles, I would like you please to create a perfect square from the expression x squared and positive 4x's. And then you're going to draw your solution below, even if there's a piece missing. Right? So what does this look like? Well, we have an x squared and we have 4x's here, and your job is to turn them into a square. Now, some of my students will go, oh, well, we can put one of these here, we can put one of them up here, we can throw one on the side and one on the other side, and that's kind of like a square. Well, it's kind of like someone took a bite out of the corners, but definitely it is square looking. And they are right. However, every time we've used algebra tiles, we've said that they are, and this is a fancy word here, an analog or a comparison to using the box method. So if I wanted to put x squared and 4x into a box, right, my x squared would go on the upper left. And then we had to split the x's, some number of x's on the right side and the bottom side of the x squared. And so that's what we're going to do with our algebra tiles. We're only going to put them on the bottom side and the right side. And in fact, if I take my 4x's and I stack 2 at the bottom and 2 on the right, I actually have a square. Now, it's kind of a square with a hole in it, but it's actually a little bit easier to see if you draw it in, right? I have my x squared tile, and then I have 2 x's down on the bottom. And so that tells us that the outline, the outside, would be x plus 2. Right? This outside here is x plus 2. And the reason that it's x plus 2 is because we could get 1x here and then 2 of the little ones. We'll need these later on anyway, right? 1, 2 of the little ones. And that perfectly outlines one side. And then, to outline the other side, we have x, and I'm going to need another one of these guys in a second, but that's okay. X, and let me throw this one back over here, and we take these 2 1s and put them up top, plus 2. So we could see that the outline of the square is x plus 2 and x plus 2. And if you can't see that, well, take a look. I'm going to draw my 2 other x's here. 1, 2. And then I'm going to go through and just outline everything that's around. And if I do that, hopefully now we can see that we have made a perfect square, albeit a square with a hole over here. So what would we actually have to add to our square to make this a perfect square, a non-wholly square? Well, hopefully we can see just visually here that we would need to add 4 1s, or looking back over here, these ones are coming in handy, right? I'm going to go ahead and take each one and use it to fill in this gap on this other side. And if I fill it in, now I have my, all a little bit messy, but oh well, my x squared plus 4x plus 4 makes a perfectly complete square. So our new one, x squared plus 4x plus 4, is a perfect square. And the original was just x squared plus 4x. I'm going to call this just the OG, the original. The OG was not a perfect square. We could get it close to a perfect square, but it had something missing. All right, so now that you get the idea, go ahead and try 3 and 4 with your algebra tiles or just with drawing. Now you're going to take x squared minus 6x, and you're going to do the same thing. Ready, set, go. All right, hopefully you found some success here. I'll quickly demonstrate, but it's pretty much the same, right? We have x squared, and we're going to have to split these x's. Now, notice when we're splitting our x's, in order to make a square, there have to be an even number of x's on each side. And when I say even, I don't mean an even number. I mean you need to take the total number of x's, and you have to divide it by 2. So to make a perfect square, we had to take this b value and divide by 2. B value and divide by 2. Now to fill in this missing space after the b value is divided by 2, we know it's a certain number of ones, but how many ones? Well, we have 1, 2, 3 x's on the top and 1, 2, 3 on the side. To fill in an area we multiply. 3 times 3 gives us 9. And notice that it is positive because a negative times a negative is a positive. So in order to find these number of ones, it looks like we took the x's that we split in half and then we multiplied them by themselves, right? We squared what was the half of the b. And that gets us positive 9. So in order to have a complete square here, or in order to complete the square, we need to take x squared minus 6x plus 9. And this is again our perfect square. And we got that from the original x squared minus 6x. So here we go. If you're given a binomial in the form of x squared plus bx, then the magic number, and I'm going to highlight that magic number up here, that magic number that we had to add to the end of the binomial to make it a perfect square trinomial, so this c value we had to add on here, was found by first splitting the b in half. We had to do half of b. But just doing half of b here got me 3. The number we needed to add at the end was 9. So what did we do with 3 to turn it into 9? We multiplied it by itself. Same thing, what did we do to 2 to turn it into 4? We multiplied by itself. And the way that we show something being multiplied by itself is we square it. This is, at its core, how we complete the square. And there is going to be a problem both on your knowledge check and on your test about this. It's going to give you x squared plus some number of x's, and you have to figure out what is the magic number at the end that turns each binomial into a perfect square trinomial. But now we have a formula to do that. I still think, though, that it helps you to envision what's happening. So if I want to find the number to add on here, we know we need to split our x's in half. I need to take half of 8. Right? That half of 8 is like when we did half of 6. We got 3. So picture half of 8 is 4. So there's going to be a 4 and a 4 right here. So what's the missing space? Well, half of 8 is certainly 4. But we need to square that. And because this is equal, we're going to put a square all the way through. Half of 8 is 4. 4 squared is 16. So the perfect square trinomial that starts with x squared plus 8x needs to end in plus 16. Okay, go ahead and try the rest of these, and I think by the end you'll understand why this formula is pretty useful, and then we'll move on to the next part of today. Ready, set, go. All right, we're back. The next one's very similar to A. Now it's negative 8x, so I just need to do half of negative 8, which is, of course, negative 4. Don't mind that extra negative there. And then we need to square the result. A negative times a negative, though, brings us back to a positive, which is why when we complete the square to make a perfect square trinomial, it is always adding at the end. Okay, what about the rest of these? Well, we need half of 12, and then we'll need to square that. Half of 12 is 6. 6 squared, 36. And can you picture that? 6 x's and 6 x's outline a gap that 36 ones would fill. Okay, same thing here. Half of negative 14, and then square it. So half of the b term is negative 7. Negative 7 squared, positive 49. And now things get a little bit trickier. Not too bad, but a little trickier, because now we have 1. And this is where our algebra tiles kind of break down. They still work, but now we just have, maybe I can show it easier on this side over here. I'll just show it with this guy. We just have 1x, and we have to split it in half. So that actually still works. You just have to imagine cutting this rectangle in half. So you'd have a skinny piece that would go on the bottom and a skinny piece that would go on the side. So we still have to do, and I'll actually take advantage of the space at the bottom of this page, we'd have to do half of 1 first. And half of 1 is just 1/2. Then we have to do 1/2 squared. And don't forget that 1/2 squared means 1/2 times itself. Many of my students think that 1/2 squared is just 1. They're like, oh, half times a half, that's a whole. Well, half plus a half is a whole, but half of a half, I mean, imagine that you had half of a cake, and then you ate half of the half that was there. How much is left? Well, that is certainly a quarter. You multiply fractions straight across. So x squared plus 1x plus 1/4, or 0.25 if you prefer that decimal. All right, and now negative 5x. Same idea. We have to do half of negative 5 and then square it. We can go decimals this time if you'd like. Half of negative 5 is negative 2.5. I don't know negative 2.5 squared, but I do know 25 squared is 625. And then I'm just going to move the decimal 2 places in because we have 0.5 and 0.5. So I think plus 0.625 would give us that perfect square trinomial. So again, most of the perfect square trinomials will deal with having an even number for the b value, which makes things pretty easy. But we should be able to extend that half of b squared to find that magic number for any b value in the middle. All right, moving on. Factoring a perfect square trinomial. Now, the first part of today was just figuring out what number needed to go at the end of a binomial to make it a perfect square trinomial. The reason that we want to complete the square is because when you complete the square, you make something that factors. Think box method. But not only does it factor using the box, it factors very easily and quickly. Because our box in this case is a square, it means that this is going to factor with the same width and length. So I'll go ahead and show you what I mean using the box. Right? So we would go through and we would take our x squared and our positive 4. We are looking for two numbers to split up the 4x. And of course, we want those two numbers to multiply to equal the diagonal 4x squared. When you do this perfect square trinomial, these numbers will always be the same, which means these numbers adding and multiplying will also be the same. And I think this case it'll be 2x and 2x, won't it? There we go. So to find the outsides, to put this in factored form, x and x, 2 and 2, and so we end up with x plus 2 times x plus 2. And in fact, people would write that even more simply. They would just say that that is x plus 2 squared. Not bad. So anytime we get a perfect square trinomial, you should expect it to factor as something times itself. So let's go ahead and try that same process as one with the other perfect square trinomial. Ready, set, go. Okay, well if you did everything correctly, and I'm going to go ahead and just show you here with the box, might as well go more in depth, and if you're comfortable with this, you can skip right to the end, not a big deal. We're going to do our x squared and our 9. We know our two numbers have to split up the negative 6x, and they have to multiply to equal 9x squared. We also know they're going to be the same number, so to multiply to equal 9, 3 and 3, but 3 plus 3 isn't negative 6. They will both need to be negative. They have to be the same number. Then we find the outsides, and we come up with x minus 3 and x minus 3. X minus 3 times itself, or as it's more commonly written, x minus 3 squared. Now, take a look at what we've done here, right? You split the x's in half. We took half of the b to get these guys, right? We split the x's in half. And that half stayed all the way through, right? Stayed here, stayed at the end. So if you're actually given a perfect square trinomial, and you know it's a perfect square trinomial, which you will, you'll have completed the square, then you can actually skip to the factored form. You could go straight from here to the answer and skip all this stuff in the middle. How can you do that? Well, it's because the factored form directly relates to the b value. It's just half of your b, right? You had to do half of the b first. You had to split your x's in half, and that same number in half is what ends up on the outside. So let's try and put it all together. Without using our algebra tiles, find the magic number that first turns each binomial into a perfect square trinomial. Then write the trinomial in factored form. So the first thing we want to do is we want to do x squared plus 8x plus the number that makes this a perfect square. And we know how to do that, right? Our number, we just take half of 8 and then square it. And so half of 8 is 4. 4 squared is 16. So x squared plus 8x plus 16 is a perfect square. Then you could use the box method up above, but now that we know our shortcut, this perfect square trinomial, we can skip right to our factored form. We just need to take half of b, which is 4. And so, and I should rewrite this with a little bit more room, my factored form is x plus 4 squared. If you multiply this out, you'll see that there's an x squared, there's 8 x's and 16 at the end, but isn't it quite a bit faster just to realize you can just do half of b and get there for the answer? So let's try the next couple a little bit faster. X squared minus 8x plus what? Well, half of negative 8 is negative 4, and negative 4 squared is again, 16. That's easy. And our factored form, well, half of negative 8 is negative 4. We do need negatives here. It's got to be different than this guy, right? And there's our factored form. A couple more. X squared plus 10x plus what? Well, half of 10 and then squared. That's got to be 5 squared, which I think is 25. So x squared plus 10x plus 25 is our perfect square trinomial. We completed the square to get there. And then the factored form is easy. Half of 10 is 5, and we're set. So at any point, you should pause me and try the rest of these on your own, but I'll keep running through them. X squared minus 16x plus something. We need to find half of negative 16 and then square it. So that's negative 8 squared, which is actually a pretty large result. I think it's 64. There should be an x there. Whoops. And our factored form, well, half of negative 16 we already saw was negative 8, so this factors to x minus 8 squared. All right, back to our odd numbers. This could be a little bit more challenging, but now that we know our formula is not too terrible, right, we're going to do half of 3, which is either 3 halves or 1.5, your choice. I'll keep it as 1.5. I feel like decimals make people a little happier. 15 squared is 225, so this will be 2.25 when we add at the end. Now, if you were asked to put this in factored form, you might say, we don't factor using decimals this year, and you're mostly right. But I can factor this just so quickly without even using the box because I know my shortcut to factor a perfect square trinomial. Half of 3 is 1.5, and so there we have it. The factored form is x plus 1.5 squared. One of the very few times we're going to use decimals. So let's do our last one, x squared minus 1x. We're going to need to add something at the end. To do that, we take half of negative 1 and square it. Half of negative 1 is negative 1/2. Negative 1/2 squared is 1/4. All right, so what's the factored form here? Well, half of negative 1 is negative 1/2, or negative 0.5 if you would like. And there we have it, the factored form. So we just factored 6 equations super quickly, right, over maybe 4 minutes, and we didn't even have to use the box. Now don't forget, you can still use the box, but the whole point of a perfect square trinomial is that it factors beautifully and makes your life easy. Now, we have a couple parts to go, and then we're pretty much done for the day. So let's chat with part 3. We found that if you started with x squared plus 4x, you could end with a perfect square trinomial x squared plus 4x plus 4. However, those two equations aren't equal. We can't just start with an equation that has a gap of 4 and then say, oh, well, we'll just give it 4 more. That changes the equation, and in math, we don't like to change equations. We like to keep them equal. And I think we can keep them equal in a couple different ways, right? If our OG equation, I'll keep using that terminology, was x squared plus 4x, and our perfect square was this guy, and that perfect square is helpful because it factors so well, what can I also do to this side to keep everything equal? Well, the OG just has an x squared plus 4x. This side has an extra plus 4. But to balance an equation, if you add 4, couldn't you just subtract 4 right on back off? And when you combine your like terms here, you have what is the original equation. Now, you wouldn't actually want to combine like terms here. It's one of those rare cases where we don't want to do that because we're going to want to factor this. So there's going to be an extra minus 4 hanging out at the end. But we do need that to keep everything balanced. The other thing we could do is we could actually change the OG equation. We could say this is our perfect square again. That's this guy right here. So if we realized that we needed to add 4 here, couldn't you just add 4 to the OG equation, right? Add 4 to the other side, and now they are both the same? Because in math, as long as you give both sides the same thing, it's good to go. All right, let's pretend this says 2 right here. Let's go ahead and do the same thing here. If you started with x squared minus 6x, and you said, I want to make this a perfect square trinomial by adding 9, then you can, but you better make sure you subtract the 9 back off. Or, and we're going to leave a bit of a gap here, if you had x squared minus 6x and you said, well, I know x squared minus 6x plus 9 is a perfect square trinomial, I want an extra plus 9 here, you can do that as long as you add 9 to the other side too. And so really for the rest of class today, I'll try to alternate back and forth because I don't know if one's any better than the other. I'm either going to add that magic number and then immediately subtract it back off, or I'm going to add the magic number on one side and do the same thing on the other. Okay, so let's practice. If we have x squared plus 8x, let's first make it a perfect square trinomial. And let's do it with subtraction. So this means I'm going to have x squared plus 8x plus something. Okay, now the plus something is always about the b, so we need to do half of 8 and then square it. Half of 8 is 4, 4 squared, 16. So I know x squared plus 8x plus 16 is a perfect square trinomial. I also know that there's still an equals 0 over here. To keep everything balanced, as all things should be, I'm going to go ahead and subtract 16 back off. Then our factored form only deals with the perfect square trinomial. X squared plus 8x plus 16 factors into x plus 4 squared, right? We just do half of 8. And then there still is the minus 16 and still an equals 0. Okay? If you wanted to do it the other way I was mentioning, we'd have x squared plus 8x still plus 16. But then instead of immediately subtracting 16, we'd say, well, you could add 16 on one side and you could add 16 on the other. That's totally allowed, right? This stays balanced if we give both sides 16. Then the factored form is just going to affect this left side, x plus 4 squared. The right side, we might as well combine our like terms. 0 and 16 makes 16. Can you see that these two are the same, right? Just done in a slightly different way. Go ahead and try b over here. And then we'll conclude this little exercise, get some practice in, and call it a day. All right, hopefully you're back. Here is part B. First, we're going to do this with subtraction. So x squared minus 6x plus what number makes it a perfect square? Well, we need to do half of negative 6 and then square that. So negative 3 squared, which is positive 9. But if I add 9, you better subtract 9. And then don't forget there's still the rest of the equation that equals 5. We can quickly factor this. X minus 3, half of negative 6 squared. And there still is a minus 9 and still an equals 5. What about if we did it with adding to the other side? X squared minus 6x plus 9, perfect square trinomial. And then on the other side, there was still an equals 5. If we add 9 to one side, we better add 9 to the other. And then factored form, x minus 3 squared equals 14. Can you see that these are the same, just done in a different way? All right. The very last part of today is we want to make sure that we don't let other values get in the way of completing the square. The only two terms you need to focus on when you complete the square for a trinomial are x squared and bx. The plus c and anything else there do not make a difference. So for example, if you had the expression x squared plus 10x plus 3 and you needed to complete the square to make this factor, this certainly does not factor, all you need to look at are the x squared and the 10x. The plus 3 is just something extra. It doesn't matter at all for us, right? So we'd go through and we'd say, well, let's complete the square. So we'd do half of 10 and then square that. So 5 squared, which is, of course, 25. Then we can say, well, there still was a plus 3 there. Great. I added 25 in addition to the 3. The 3 doesn't matter. To keep everything balanced, though, if you add 25, you better subtract it back off. Then we're just going to focus on the perfect square piece. Half of 10 is 5. X plus 5 squared. And then we could probably combine like terms here, right? 3 minus 25, that's negative 22. And there we have it. Completed the square. We got to ignore the last term. It didn't matter. And it combined with that balancing factor at the end. Want to look at one more? X squared minus 12x minus 1 equals 5. All right, so we're just going to focus on completing the square first. X squared minus 12x. We need to do, of course, half of negative 12 and then square that. That gives me negative 6 squared, which is, of course, 36. Now we have a perfect square trinomial, x squared minus 12x plus 36. There was still a minus 1 from the beginning, so that didn't go anywhere. And if you added 36 to one side, you better add 36 to the other. We could have, of course, also subtracted off 36 on the same side. Then we factor, right? Perfect square trinomial, easy to factor, x minus 6 squared minus 1, and we should probably combine like terms here to get 41. Now, at long last, finally, why did we spend so long on completing the square today? It seemed like last class, all we needed it for was just to make it easier to find our vertex, and that is one use. But actually, completing the square is one of the most useful equation solving and rewriting techniques in algebra. Because what completing the square allows us to do is it allows us to take an equation that has multiple x's. Do we see the two different x's? And we've talked about this before. When you see an equation with multiple x's that don't combine, the only way we had to solve it was by using the box. But this unit is all about non-factorable quadratics. You won't be able to use the box on something like this. But by completing the square, we had two different x's, right? Look at what happened when we finished this problem. After we completed the square, how many x's do you see in here? I just see the 1. And I see a whole bunch of numbers attached to it. 6 is subtracting in parentheses, there's a square, and there's a 1 that's subtracting. But if we wanted to continue to solve for x, now we can use SADMAP. There's only a single x left. That's pretty awesome. So the original problem wasn't solvable by any means we know. The box won't work. But after we finished completing the square, now we can focus on SADMAP to isolate x. So that is our big reveal for today. To complete the square, you follow the steps we went through, and then now we get back to topic 7, and all we have to do is follow SADMAP to solve. So it's time to put everything together. Your goal is to solve each of the 6 problems below using any method. Now, all of them are going to have multiple x's here, which means we can't use SADMAP right away. However, if you look at the answers, some of the answers are nice integer numbers, while others have square roots. If you have an answer with a square root, that's an indicator that the problem is not factorable, which means you can't use the box. So on those square root ones, you're certainly going to have to complete the square. But on ones with nice integer values, I would suggest you just use the box. Okay? One last thing. If you are going to use the box, your equation has to be equal to 0, right? So if we're going to use maybe the box on this guy here, it has to be equal to 0. And if it's not equal to 0, you better make it equal to 0 before you try that box method. Otherwise, you're not going to get the right answer. Speaking of answers, since we have the right answers, we are of course looking to show the work to match the right answer. All right. Good luck to you. There are 6 questions. If you get stuck, unpause, come back to me, and I will help you all out. Ready, set, go. All right, you're back. I'm going to tackle the problems with the box first because that's old school, and then we'll jump back to the new stuff for today. So, box method, we equal 0. Very exciting, and in fact, I don't even think I need the box here because there's a 1 in front of x squared. In fact, for each of these, we don't need the box, so I will show the box for the first one, but then the other 2, we're going to do it faster. We're all about efficiency here. So, box method-wise, I'll try to show this over on one side. If we're going to do that, I think there'll be room down below. Not a big deal. So, I'm going to go ahead and put the x squared and the 16 inside, and then we need to split up that 10x, don't we? So add to make 10x and multiply to make 16x squared. Okay. Let's see, I think that's looking like 8 and 2, doesn't it? 8 times 2 is 16, 8 plus 2 is 10. And then we find the outsides. When we find the outsides, and this is what I meant about there being a 1 here, you'll find that the outside numbers just match the 2 numbers that we found, x and x, 2 and 8. So we can go through and just say, well, this becomes x plus 2 times x plus 8 equals 0. Once we're here, do you remember how to solve? This is from topic 9. This is our 0 product property. We take x plus 2, set that equal to 0. X plus 8, set that equal to 0, and then we go through and solve each one. Subtracting 2 from each side gives us an x of negative 2. Subtracting 8 gives us an x of negative 8. And you'll notice those match the 2 answers at the bottom. Alright, let's take a look at problem 4 because we have those, again, nice integer values. If we're doing problem 4, we need to make sure the equation equals 0 first. We know how to do that. We practiced this plenty last unit. We subtract 4 from each side. X squared plus 2x minus 24 equals 0. And then I'm actually going to go ahead and skip right to my factored form because I realize that there's a 1 in front. So we are still going to need 2 numbers to split up the 2x, but I'm just going to say add to equal to here. And they do have to multiply still to equal negative 24. And you could say times 1, but that doesn't really make a difference. But from here, we should be able to factor quickly. This to me looks like negative 6 and positive 4. No, other way around. 6 and negative 4. Because 6 minus 4 is 2. 6 times negative 4 is negative 24. And bam, we're factored. X plus 6 times x minus 2. Ha! Nope. Times x minus 4. There we go. Alright. 2 equations. X plus 6 equals 0, or x minus 4 equals 0. Subtract your 6 from each side, add your 4 to each side, and we've matched our answer. Okay. One of these box methods to go. Also not equal to 0. How dare they? Let's add 5 to each side first. X squared plus 1x, and then minus 30 equals 0. Factored form time. We'll need two numbers to split up the 1x in the middle, and they're going to multiply to make negative 30. Numbers that are 1 apart that multiply to make 30, that's got to be 6 and 5, doesn't it? Which one gets the negative? Well, this is positive, so the positive sign matches the larger number. 6 minus 5 should do it. X plus 6 times x minus 5. And then make your two equations. X plus 6 equals 0, or x minus 5 equals 0, and solve. Negative 6, positive 5. Woo! Okay, we've done our review for the box method, our factoring method. Now let's jump into that completing the square. In order to complete the square, because the box method won't work, you can try it if you don't believe me, but it's not going to work, we do not need this to be equal to 0. I'm just going to focus on the two important terms, the x squared and the bx. And to complete the square, we're going to do x squared plus my bx plus that magic number. And then we'll do plus 5, we'll subtract off the magic number and set it equal to 1. What is the magic number? Well, we need half of 6 and then squared. Half of 6 is 3, 3 squared is certainly 9. X squared plus 6x plus 9, we also better subtract off the 9. Then we factor. We know how to factor this quickly. X plus 3 squared. Combine your like terms. 5 minus 9 is 4 equals 1. Hey look, it's SADMAP time. We only have one x left. We've successfully completed the square. Let's start with that addition and subtraction. And you have this minus 4 that we'll undo by adding 4. Sound effects make everything better, I'm sure. X plus 3 squared equals 5. We can't undo the adding 3 yet because that's inside the parentheses, which is last. We can, however, undo the exponent with a square root. Remember this? A square root undoes a square. That gives me with x plus 3 equals, and don't forget a square root has two answers you need to consider when you write it in, plus minus. Last but not least, to finish getting x alone, we should probably subtract that 3 from each side. When we do that, I'll write this just over here, we have x alone now. Negative 3 and square root of 5 can't combine. One has a square root, one doesn't. So I'm just going to set the negative 3 right in front of the plus minus square root of 5. And lo and behold, this matches our answer. Pretty awesome. 2 to go. X squared minus 8x plus 8 equals negative 1. Well, I think the first thing we should probably do is, and I'll just write this over on the right here, I think, is we should probably go through and add the 1 to each side, right? Add 1, add 1. So that will give me x squared minus 8x plus 9 equals 0. Though, honestly, I'm not quite sure why I did that, because I mentioned earlier, you don't need to have your equation equal to 0. My brain just went into full automatic mode and did silly stuff. So I didn't need to do that. Let's just focus on completing the square. X squared minus 8x, we need to do half of negative 8 and then square that guy. Half of negative 8 is negative 4. Negative 4 squared is positive 16. All right, there still is a plus 9. There still is an equals 0. And because I didn't leave myself room, we'll do it this other way. If you add 16 to one side, you better add 16 to the other. Let's factor. X minus 4 squared. We have a plus 9 equals 16. And now we can isolate x. We need to subtract our 9 from both sides. And if you do that, 16 minus 9 is going to give us 7. That's looking good so far because I see a 7 and a 4 in our answer and a 7 and a 4 in our problem. We undo the square with a friendly square root. X minus 4 equals, and in front of the 7, plus minus. And last but not least, we need to add 4 to each side. 4 is, of course, not a like term with the square root of 7, so that positive 4 just hangs out in front of the square root of 7. It could go at the end, too. You could put a plus 4 here. Nothing wrong with that, but they wrote their 4 in front of the square root, so I'm just trying to copy what's there. And I think we have our answer. Okay, last problem for the day. X squared plus 4x minus 8 equals 0. It's already equal to 0. Very nice. Didn't have to be. Let's complete the square. x squared plus 4x plus a blank. And then I'm going to subtract the blank right back off. And then don't forget that there is a minus 8 equals 0. Half of 4 is 2. 2 squared is 4. Just like what we did on the previous pages, x squared plus 4x plus 4. And then if we add 4, we better subtract 4. Factoring wise, x plus 2 squared, negative 4 minus 8 is negative 12, equal to 0. Let's keep cleaning this up. X plus 2 squared, I'm going to add 12 to each side. Then of course we take our square root. Leaves me with x plus 2 equals, don't forget the plus minus square root of 12. Last and hopefully least, all we need to do is subtract our 2 from each side. And when we do that, we get x equals negative 2 plus or minus the square root of 12, which doesn't match our answer, because instead of the square root of 12, they have 2 square roots of 3. But at least the negative 2 matches. That, of course, brings the question, how did they get 2 square roots of 3 from the square root of 12? And hopefully you remember, sometimes we have to break down a square root, right? We take that square root of 12 and we break it down. I would probably break it into 4 and 3. 4 is a perfect square. And then if you wanted, you could keep going to 2 and 2. But again, what I would do is I would take the square root of 12 and say, ha, we could rewrite that as 4 times 3, because I know the square root of 4. The square root of 4 is 2. I don't know the square root of 3, so that stays. You could have found the same answer by taking your pair outside and putting the loner inside. But either way, I think that gives us an answer of negative 2 plus or minus. Instead of the square root of 12, we broke it down into 2 square roots of 3. So hopefully you see how everything connected here from the very first page of taking half of the b and squaring it. That gave us a perfect square. Perfect squares were easy to factor. And then once we knew how to factor, we could solve using SADMAP. There is a lot that goes into completing the square. And in fact, we should learn how to complete the square with other numbers besides 1 in front of x squared. But this year, we don't force that on you. This year, we just do 1x squared plus other numbers. In Algebra 2, you guys will deal with completing the square with other values of a. Okay. Also, if this completing the square method seems pretty tricky for you, then next class is for you. Next class, we're going to learn our second method to solve these non-factorable quadratics, and it's a little bit more straightforward than what we did today. However, you still need to know it today. Half of b squared helps you complete the square. So thank you for tuning in, and hopefully you found today interesting and useful.